Welcome to This Explainer. Today, we're going to completely transform how you view the ground beneath your feet. We usually think of the crust we stand on as permanent, right? Just solid, unchanging rock. But deep down, it is constantly being subjected to literally unimaginable forces in the Earth's ultimate geological kitchen. So let's jump right in and demystify the absolutely incredible process of metamorphism. Okay, let's get the foundational concept down first. Metamorphism is essentially the Earth cooking rocks deep underground, but without actually melting them. For this to happen, these rocks have to be buried deep, usually below about 3 kilometers in the crust. Down there, they're getting crushed in massive mountain-building events, or they're interacting with serious igneous activity. But here's the absolutely crucial takeaway. This entire alteration, the changing of mineral types, shapes, and textures, happens entirely through recrystallization in the solid state. No melting allowed. Think about this process like adjusting the dials on your oven. A prograde reaction turns the heat and pressure way up, driving the transformation forward and sometimes squeezing volatile phases like water completely out of the system. But what happens when the rocks eventually cool back down? That's a retrograde reaction, where temperatures and pressures drop. Interestingly, though, retrograde is actually way harder to achieve. Why? Well, because energy is leaving the system, the rock lacks the activation energy it needs to easily reverse the reaction. Plus, it would need to somehow get all those lost water vapors back. And honestly, this is exactly why we can find stunning, high-pressure metamorphic minerals sitting perfectly preserved right on the Earth's surface today. Here's our menu for today's explainer. We'll start with the Earth's kitchen, move on to recipes and ingredients, then look at 3 specific cooking methods: dynamic, contact, and regional metamorphism, before finishing up with the ultimate melting point. All right, Section 1, the Earth's kitchen, focusing on recrystallization in the solid state. If you ever done pottery, you actually already get this concept. Just like baking wet, soft clay in a kiln creates a hard, dense brick, metamorphism changes a rock's minerals and texture while keeping its fundamental chemical recipe exactly the same. Sure, maybe some water is lost as vapor, but the bulk chemical composition you start with, that is the exact same chemistry you end up with. Section 2, recipes and ingredients. Let's talk about protoliths and metamorphic grade. In the geo world, we call the original starting rock ingredient a protolith, and the final metamorphic dish you get out of the oven depends entirely on this starting ingredient. Generally speaking, protoliths fall into one of 5 distinct chemical categories. You've got your ultramafic and mafic rocks, which are super rich in magnesium and dark minerals. Then you have quartzo-feldspathic rocks, like granites and sandstones. Next are carbonate rocks, like your limestones. And finally, palitic rocks, which are basically just fine aluminum-rich shales. So the big point here is that a single ingredient, let's take a pellolite, for example, will transform into completely different mineral assemblages depending on the metamorphic grade. And grade just means how intense the pressure and temperature conditions got. Looking at the pellolite, at a low grade, it just cooks into chlorite. But crank that dial up to a high grade, and that exact same rock transforms into complex minerals like cordierite and sillimanite. Behind all of these incredible transformations is a pretty simple law of nature: laziness. Seriously, the rock is just seeking the path of least resistance. In thermodynamics, we call this minimizing Gibbs free energy. You see, every combination of minerals has a specific free energy level that shifts based on the outside temperature and pressure. The rock simply reorganizes its internal structure, recrystallizing to find the most stable, lowest possible energy state for whatever extreme environment it's stuck in. Moving on to Section 3, dynamic metamorphism. I like to call this one the Earth's blender. Let's see how this blender actually works. Imagine a massive fault line where entire tectonic plates are just grinding against each other. The rocks here are caught under immense shear stress and pressure, but surprisingly, not a lot of heat at first. The rock is mechanically pulverized into jagged fragments, creating what we call a breccia. As the fault keeps grinding, those fragments are milled down further and further. Eventually, the sheer frictional heat of this geological blender causes the pulverized dust to recrystallize, forming a highly deformed, strongly banded rock known as a myelinite. Section 4, contact metamorphism. This is our magma oven, where we bake the country rock. Unlike the blender, this process is all about heat. Picture a massive plume of incredibly hot magma pushing its way up into the cooler, unaltered crust, which geologists call the country rock. This magma intrusion acts exactly like a giant oven element, radiating intense heat outward. It literally bakes the surrounding rock, creating an altered cooked zone called a metamorphic areole. Depending on how big the magma body is, this baked zone usually stretches a few hundred meters wide. Let's take a little walk, starting from the cool country rock and heading directly toward the intense heat of that magma. We'd see an unbelievable gradient of change. Let's use a shale as our example. Out on the cool edges of the areole, the heat is just barely enough to start creating tiny new mineral spots. But as we step closer to the heat source, those minerals grow into massive, visible crystals called porphyroblasts. Think striking garnets. Finally, right at the contact point where the heat is absolutely blinding, the rock is completely recrystallized into a tough, splintery material called hornfels. All of its original sedimentary history is just entirely wiped out. This magma oven also gives us some of our most famous building materials. For instance, when a limestone gets baked in contact metamorphism, it recrystallizes. Any fossils it had are completely obliterated, and it turns into the beautiful, sugary texture of marble. Similarly, bake a quartz-rich sandstone, and those rounded grains literally weld together into a super tough interlocking mosaic, producing quartzite.
Section 5. Regional Metamorphism. Welcome to the pressure cooker of tectonics and mountain building.
Now, we are talking about massive regional scales, like the Damara Metamorphic Province in Namibia, or the Namakwa Natal Province. Deep below continental mountain ranges, rocks undergo immense tectonic burial. Over literal epochs of time, this slow, crushing pressure forces a clear textural progression. In the early phases, you get a phyllitic texture, where tiny mica flakes align to give the rock distinct cleavage planes. As the pressure steadily mounts into the intermediate phase, a wavy schistose texture forms with much larger grains. Finally, at the climax, you get a gneiss texture. The squeezing is so intense here that the minerals literally separate out into stark, distinct light and dark bands.
What's really fascinating here is that each of these rocks acts like a giant geological barometer. Slate tells us the rock experienced low temperatures but enough pressure to create strong cleavage. Phyllite tells us the temp bumped up slightly, giving it a cool, rolling surface. Schists show us even higher grades, where the new minerals are big enough to see with the naked eye. And gneiss, that represents the extreme high temperature and pressure environments. Oh, and if those bands in the gneiss get deformed and broken into little lens-shaped clots, we get what's wonderfully called an oggen gneiss.
Finally, Section 6. The ultimate melting point. Let's see what happens when the kitchen simply gets too hot. When rocks hit the absolute upper extremes of metamorphism, they experience a really wild process called an ataxis. This is the onset of progressive partial melting. Usually, right around 650 degrees Celsius, assuming there are some hydrous fluids around, the lighter quartzo-feldspathic bands in the rock actually hit their melting point and turn to liquid magma. Meanwhile, the darker, tougher refractory minerals just stay completely solid. This partial melting creates an absolutely stunning hybrid rock called a migmatite. Seriously, it almost looks like swirled taffy because it is literally half melted. It's made up of light-colored bands called leucosomes, which was the liquid melt that eventually cooled and solidified, mixed right alongside dark bands called melanosomes, which are the solid, heat-resistant mafic minerals that refuse to melt. It is literally a rock frozen right on the edge of its own destruction. But heat and pressure aren't the whole story deep in the crust. Remember how we said metamorphism doesn't change the bulk chemical composition of the rock? Well, there's always an exception. Sometimes extremely hot, volatile fluids inject into the rock and entirely rewrite its chemical recipe. They do this by carrying in new elements or washing existing ones away. This rule-breaking process is called metasomatism. It creates chemically altered zones called skarns, which are super important for us because they often produce highly valuable deposits of minerals like tin and tungsten. So, having seen how the Earth relentlessly crushes in its dynamic blender, bakes in its magma oven, and squeezes the crusts in its regional pressure cooker, I'll leave you with this final thought. If extreme heat, pressure, and fluids can completely melt, deform, and chemically rewrite the very identity of stone, is the ground you're standing on right now truly permanent? Or is it just a temporary ingredient, quietly waiting for its turn in the kitchen for its next recipe? Thanks for joining me on this explainer, and keep questioning the world beneath your feet.